like I mentioned, for review, we've looked at graphing exponential functions of the form a, b, x to the, b to the x minus h plus k. Sorry, that was a little sloppy. A, b to the x minus h plus k. Those are the forms for our exponential functions, and we're going to actually look at deriving those functions today. I took an example from your previous notes here where we have all kinds of things going on with a 4 as an a value, a 2 as a b value, a minus 3 where our x minus h is, and then we have a plus 2. If you remember, the a and the b is the thing I always forget. I know usually you're pretty good about remembering that A represents stretches and compressions and reflections, but it's also remembering that it represents your y-intercept, right? It's your y-intercept. And then your B is your parent function. It also determines your direction. So if you look on in the blue box, it tells you, okay, what happens when B is greater than 1, or if B is in between 0 and 1, it's just gonna flip it in terms of going left and right versus right to left. So if we look here, I mentioned when we first did this that we have to identify what our parent function is, and then we can apply the transformations. I find that the easiest when you have something that has a lot of things going on that's really busy. So let's just identify our parent function for number 1. What is our parent? Yeah, 2 to the x. Yep, 2 to the x. So let's just make the chart for 2 to the x. And then just apply the transformations. So I know that looking up in my chart that I have a y-intercept at an a value. Well, I don't have an a value other than 1, an implied 1 in front of the 2. So my y-intercept is 0, 1. So I can start there. And then I can just plug in some easy values. When I plug in 1, I get 2. When I plug in 2, I get 4. When I plug in negative 1, I get 1/2. And when I plug in negative 2, I get 1/4. Now I'm going to apply the transformations for this one. That's being stretched by a factor of 4, that's being horizontally shifted 3 to the right, and that's being vertically shifted 2 up. So you're going to take your x value, you're going to add 3 because you know you are moving to the right 3 units. And then your corresponding y values, you're going to multiply them by 4 and then add 2. So you're going to take 4 times a 4th and then add 2. You're going to take 1/2 times a 4th and then add 2. You're going to take 4 times 3 and then add 2. 4 times 4. Add 2, and then 4 times, 4 times 2. Let me erase this. Mess this up. 4 times 1 plus 2, 4 times 2 plus 2, and 4 times 4 plus 2. Let's just write out some points here. So I get 1, 3, 2, 4, 3, 6, and 4, 10. Let's just graph those. 1, 3, 2, 4, 3, 6, I know that that plus 2 is my horizontal asymptote. So I'm going to go ahead and draw in my horizontal asymptote. And then I'm going to connect the dots. All right, so not hard. If I gave you just a pop quiz on that, would you have remembered how to do that? By hand, maybe? Yeah. Again, this is just to keep things in mind, just a reminder. Like I said, I always forget which is the y-intercept and which, like what the A and the B do beyond just stretching and compressing, so you just take a look at that. Now, we talked about limits, this concept of limits and the idea that limits are essentially your horizontal asymptotes. So if you were to take the limit of this function and you were going to find the limit as x approaches negative infinity, because your x values are going towards negative infinity, looking at the direction of the graph, the limit would be 2. Okay. So in other words, if they told you for a complicated function as x approaches negative infinity, if you didn't remember that that 2 is your horizontal asymptote, but you were told this, then you get 2. Because if you think about it, if you take a negative number and you subtract 3, you'll get another negative number, right? And actually, this will be moved to the denominator. Because anytime we have a negative exponent, we move it to the denominator, right? So what ends up happening is we're putting bigger and bigger numbers in the denominator. So this actually is going to be 0, right? And this will be 2, this approaches 0, and then we have that plus 2. Does that make sense? Because as long as this exponent is negative, it gets moved to the denominator, and you're increasing how negative it gets, which means you're increasing how large the denominator is. So as you approach negative infinity, you get a smaller and smaller number, and that smaller and smaller number gets closer and closer to 0. So this cancels out, and you just get plus 2. Questions? Okay, let's look at graphing logs. Because again, that's been a while too. Now if you had a paper 2, it's easy, right? You just plug it in your calculator. And usually they don't necessarily want you to just draw a detailed graph. It's usually just a sketch. But let's say it's paper 1. If you know the graph for 10 to the x, then you know the graph for log 10 of x, because they're inverses. Remember that exponential functions and logarithmic functions are inverses, which means they are reflected over the line y equals x. Most of you remember that, which is really good. I like to see that on your exams. If you wanted to just double check and make sure, remember the process of finding an inverse. To find an inverse, you switch the x and the y's, and then you solve for y, right? And to get rid of the base 10, you have to do log base 10 on both sides. So your inverse is equal to log base 10 of x. So we know that in inverses, the domain and range is flipped around. So I just make a table for 10 of x and I just flip it around. And that's how I graph log base 10 of x, right? So, because I was always a student who, when I saw logarithm, I always forgot if there was like a technique involved or whatever. But just remember that if you know the exponential, then you know the log. It's just flipped around. So let's just look at y equals 10 to the x. Look at a few points. You don't even have to look at many. I'm just going to look at 3 points. You plug in 0, you get 1. Plus, based on the rules that you saw in the beginning, this a value is 1. So, and then you plug in 1, you get 10. And you plug in -1, you get 1/10. Therefore, y equals log 10 of x is going to be reversed in its domain and range. Your x value is going to be 1/10, 1, and 10, and your y value is going to be -1, 0, and 1. And then you'll graph. So 1/10 is really, really tiny. Just gonna guess about right there. 1, 0, and then 10, 1. It's about right there, and then you're going to graph. So it's important to remind ourselves about the relationship between exponential functions and logarithmic functions as we try to recall the things that we've learned about previously in our syllabus. Questions? Yeah, not too bad. So the goal again is to derive these functions now. Actually, the rules for deriving log and exponential aren't that bad. And actually SL, if you're in HL, you'd have to learn all the different rules, but for SL, you only learn 2 of them, and they're very straightforward. So this problem. Remember when I asked you specifically how you did this? Emily said you just substitute x in and you factor it like normal, right? Because you're able to use basic factoring techniques, and then you just plug your e to the x back in. Substitution is what we use when we have a complicated function. You're going to need to use it anytime you look at something in it, when you know you have to use a chain rule, or even beyond that, if it's more complicated. You want to use substitution just because it makes the process easier for you. It's just a method. It's a method. Now that we've taken a moment to review a little bit about the basics, graphs, and some of the algebraic processes, again, take time if you don't remember. We're going to take a look at the derivatives. We're lucky in this class because we're actually only going to work with natural log and with e to the x. And these derivatives are pretty easy. The derivative of e to the x is e to the x. Doesn't change. The derivative of e to the x is e to the x. The derivative of the natural log of x is 1 over x. Now, situations can get a little complicated because we sort of have to apply the chain rule when we're working with e to the x, because that, whatever it's raised to, that's, again, a function inside of another function. Your big picture is the e, right? And your small picture is whatever it's raised to. Does that make sense? Now, if you go to the bottom here, it tells you specifically what I mean by that. If you just have e to the x, then your derivative is just e to the x. But if you have anything else, you have to treat it like the chain rule. You take the derivative of the big picture, which is just itself, right, times the derivative of that inside or smaller picture function, which is the derivative of f of x. Does that make sense? So this is really a chain rule, extension of our chain rule. So we're going to spend today just practicing that, and then tomorrow we're going to look at natural logs. But if you want to look ahead and you understand this already, you can. If we go back here, remember that e to the f of x is just the derivative is e to the f of x. You don't change anything, times the derivative of the inside. Now, but let's practice a few of these together. So, for A, when I want to find the gradients, remember a gradient and derivative are synonymous. They mean the same thing. So find the gradient function for y equals 2. So they want to know the function that gives you the slope of the tangent line, right? So since we're adding 2 things together, we just take the derivative of each separate part. So the derivative of 2 e to the x. Well, the derivative of e to the x is just e to the x, right? So is just 2 e to the x. If you look back at your basic differential rules, if you had a constant in front, it's just the constant times the derivative, right? When we saw those basic rules in differentiation, we saw one of the rules was if we have a constant in front of a function, then when we find the derivative, it's just the constant times the derivative. That's why it's 2 e to the x. Nothing happens with the 2. Are we clear on that? Now, for the next part, you have to use that chain rule thing because you have a negative 3x functioning as that sort of quote-unquote small picture. So that becomes plus, well, the derivative of the big picture is just itself, e to the negative 3x, times the derivative of the small picture, whatever it's raised to. What's the derivative of negative 3x? Negative 3. So let's put this together and let's look back just to clarify some things. So our final answer is negative 3 e to the negative 3x plus 2 e to the x. Remember, you don't have to simplify unless it's super easy to simplify or it's very obvious. Otherwise, for sake of time, just leave your answer like this. Rearrange so that you have your coefficients in the proper place. So, and I'll go back to this. So for the next one, for B, this is product rule because we have a product of an x squared and an e to the negative x. So we're combining two rules here. Product rule says first times the derivative of the second plus second times the derivative of the first. So first times the derivative of the second. Let me just put a little bracket here. Okay, well, the derivative of the second is what? Yep. So e to the negative x times negative 1. So I have this first times the derivative of the second plus second times the derivative of the first. Second times the derivative of the first. What's the derivative of the first? Yep, 2x. Let's just do a little bit of rearranging here. So I have negative x squared e to the negative x plus 2x e to the negative x. Okay, I see a very easy GCF here. I can go ahead and factor it out. And that's my answer. Questions? Remember, those equations are the equations you use for finding slopes of those curves. Instantaneous rate of change at a point. So C, we've got quotient rule combined with a derivative of e to the x, e to the 2x in fact. So quotient rule is low d high minus high d low all over low low. So for C, low d high, low is x times the derivative of the high, or the derivative of the numerator. What's the derivative of the numerator? E to the 2x times. Well, your f of x is 2x, right? So it's going to be, this derivative is going to be e to the 2x times 2. Right? Because your f of x is 2x. Oh, sorry. Low d high, right? So low is this, then derivative of the numerator. I meant numerator. My mistake, I'm sorry. Yeah, so it's e to the 2x times 2. So times e to the 2x times 2. So low d high minus high d low. What's that going to be? e to the 2x high d low times 1, right? All over low low, which is x squared. All right. Are we okay? Are we good? Did I do something wrong? Y, it equals itself. This is 2x e to the 2x minus e to the 2x all over x squared. And then of course you can factor out an e to the 2x pretty easily, so we're going to go ahead and do that. Okay. Do we have any questions about how I arrived at that simplified answer? So at this point, we got the technique, we just want to know why, which we'll get to. Okay, we're going to talk about chain rule with this now. So let's take a look at these last two. Okay, it says find the gradient function for y equal to e to the x minus 1 cubed. That's chain rule because I've got something cubed. So I'm going to go ahead and use my u substitution. And remember what my chain rule is. And y is equal to u cubed. So dy, the derivative of y in terms of u is equal to what? Yeah, 3u squared. And then I'm going to look for the derivative of u with respect to x. So let me write down what u is equal to. U is equal to e to the x minus 1. So the derivative of u with respect to the x is going to be what? Just e to the x. Okay. And so I'm going to substitute my u back in. So I get dy over dx is equal to, let's plug in that 3 times u e to the x minus 1 squared, and then times e to the x. So we get 3 e to the x times e to the x minus 1 squared. Yeah. It's the u substitution, the idea of u substitution. So if you go back to, like I said, when I did this, the first time I learned chain rule in my calculus class in high school, I didn't really appreciate u substitution. All I said was, oh, if it's cubed and it's going to move the 3 out front, put a square, then times it times the derivative of the inside. That's all I did. But then when we got to super complicated different derivative problems, and my teacher was telling us to use u substitution, I suddenly got the question of, okay, well, why are we doing this now? Like, what? I didn't have to do it before. I didn't appreciate it then. So introducing it now will help you understand its role in the future, if that makes sense. All right, so for B, we've got quotient rule. No, actually not quotient rule, because you can just move this up. Question, Michelle? Here. Okay, pause. Now you could, if you wanted to, you could use the quotient rule here, but since it's just 1 over an expression, just make it to a negative exponent. That's what I would do, because you know that really it's just 1 over 2e to the negative x plus 1 to the 1/2, right? Well, because it's 1 over, you can move it to the top and just make it negative, right? That's just a rule of exponents. Really, this is equal to 2e to the negative x plus 1 to the negative 1/2. You'll see on the mark scheme for one of the questions that I gave you for homework that they show 2 ways that you can do it because they have a problem that's similar to this. Now I see I've got a chain rule example, another one with a big picture, small picture. This time the big picture is u to the negative 1/2, right? So I'm going to do what I did last time, same technique. Y is equal to u to the negative 1/2 this time. And then I'm going to find dy over du. Are you paying attention, John, or are you looking at something else?
What?
Are you paying attention to the lecture, or are you looking at something else?
I'm looking at the key of this.
Okay, just making sure. Okay, u to the negative 3/2. And then your derivative of your smaller function. So our u is equal to 2e to the negative x plus 1. Right? So let me find du over dx. What's the derivative of u with respect to x? Yeah, negative 2e to the negative x, right? Excellent. Now I'm just going to put that together. dy over du times du over dx. And I'm going to substitute my u back in. Let's go here. So this is negative 1/2. I'm going to substitute my u back in, which is 2e to the negative x plus 1 to the negative 3/2 times negative 2e to the negative x. Once again, let's see. So you've got a negative 1/2, 2e to the negative x plus 1 to the negative 3/2 times negative 2e to the negative x. Do we have any questions? No? Okay, again, it looks a little complicated as far as your answer is concerned, but again, if you are taking your paper 1 or paper 2, don't simplify it unless asked. Okay, oh shoot.